So thus far, we've been talking about what it means for a function to be continuous at a specific point, right? At a specific value of x. And so now we want to introduce some definitions and terminology that will help us make sense of a statement of something like a function is continuous on an entire open or closed interval. That is, it's continuous kind of over a range of values. So here are two definitions, or technically I guess three definitions to kind of help us with this. We'll say that a function is going to be continuous from the right at a if it's the case that our right-sided limit is equal to the y value at the point. And we'll say that a function is continuous from the left at a if I can get the limit from the left to be equal to the y value at that point. So first we're just introducing these ideas, and we'll use them to understand how we talk about intervals a little bit further down below. Take a look here at the definitions in the next box. A function f is going to be continuous on a whole open interval if the function is continuous at every single number in that interval. That almost kind of makes sense. So if I wanted to take a look at a function, maybe something like a simple line, and I say, is this continuous from 1 to 2? Well, then I could kind of look at just this portion of the function and say, is the graph going to be continuous at every point in between 1 and 2? And it looks like yes. Of course, proving this more generally with the actual definition of continuity will be a bit more involved, but we'll see that in a moment. If we want to show, though, that a function is continuous on a closed interval, we have to do kind of a combination of different things. First, we have to show that the function is continuous at every point in between the endpoints. But then we would want to show that as we move towards the value of a, which would be this left point, we have to move at that from the right side. So we want to make sure that the graph is going to be continuous from the right as we move towards our starting point, our point A, or in this case, like our point 1. We would also then want to check that our function is continuous at b. But we want to check, since I'm only on this interval, that as I move towards the value of b, the end of the interval, from the left side, that I'm going to end up being continuous. So of course, understanding which direction I have to move from here is really made clear by considering a picture. Now let's go ahead and take a look here at a specific example of how I would do something like this, here in example number 6. So let's consider the function f of x equals square root of 9 minus x squared. And here's a graph of the function below. This is actually the equation of like a half circle, okay, the top half, and it's pictured here in blue. Now really quickly, I could go ahead and actually state the domain of my function of f. Remember that domain just means I'm looking for all of the different possible values of x that I can plug into my function to get y values. So in this case, I could start to see that, well, obviously some values are going to be off limits, right? Like I can't plug 4 in. If I plug in the value of 4, I'm going to get 9 minus 16. That's going to put a negative under the radical, and we don't want to deal with complex numbers in Calculus 1. So we're only going to be dealing with real numbers. So let's think here. The smallest the inside could ever be made into is the number 0. And so I can see that that would happen if I plug in negative 3 or positive 3. Anything bigger than 3 is going to force me to subtract too much. And anything smaller than negative 3 is going to force me to subtract too much. So the domain here would actually just be negative 3 to 3. Of course, this is perfectly confirmed by the picture. No big deal. Another way that you could actually go ahead and confirm this is by just trying to think about the fact that we need 9 minus x squared to be greater than or equal to 0. This means that I would need 9 to be greater than or equal to x squared. And if I square rooted both sides and rewrote this, that means I would need the square root of x squared to be less than or equal to the square root of 9. If I simplify both sides, you can see here that on the right side I'm going to get 3, and on this side I have to be a little careful. We talked about this in a previous section. The square root of an x squared is actually absolute value of x. And so now I have to solve this absolute value inequality, which would give me that x has to be between 3 and -3. So I get to the same final answer, but this would be the algebraic way I could solve for that. All right, so if this is the domain of my function, how do I start to show that this function is continuous on an open or a closed interval? Well, this is what part B is all about. I want to show this function is continuous on its domain. So I want to show that this graph here is actually connected everywhere. Now, it might seem like, well, Kyle, that's really silly. Can't I just look at the picture? But we have to be a little bit careful. How do you know, looking at the picture, that there isn't a hole in here that's just been missed? Like maybe if we zoomed in farther on it, we could see one of the holes actually being formed. So if I want to actually prove something like this, I'm never really going to use the picture to justify it. I'm actually going to have to go back and check all three of these things here. To show that a function is continuous on a closed interval, I'll show each of the following. Now we're going to start with part A, which is actually probably the hardest part here. Let's go ahead and see what we need to show. Okay, so we will start by showing that f of x is continuous on -3 to 3, the open interval. Now this is going to be kind of difficult to do because remember, in order to show that a function is continuous on an open interval, you have to actually show every single number in that interval works, right? That every single number in that interval makes the function, or the function is continuous there. But how many numbers are there inside of this interval? Well, there's infinitely many. Don't just be thinking like -2, -1, 0, 1, 2, right? I mean, there's like, what about 1.5 or 1.6 or pi divided by 17? You know, like all those terrible numbers are in there. I have to deal with all of those. Well, how in the world am I going to be able to show that a function is continuous at an infinite number of spots? I mean, I only have this much space. I don't want to just start trying every number. That's going to be terrible. So what we often do in scenarios like this is we do something like the following. First, let C represent any number in the interval -3 to 3. Let's pretend that I pulled some number out of that interval, and I'm going to check to see if the function's continuous there. I don't know what the number is, I just know it's from that interval. Okay, well now let's go ahead and check continuity. So I'll say, we see that the limit as x approaches c for my function f of x would be equal to the limit as x approaches c of 9 minus x squared. Okay, now how would I compute a limit like this? You might recall that one of our limit laws was that if I had the limit of a square root, I could move the limit to the inside of the square root. I could like tackle the inside first. Okay, but if I want to do the limit of the inside, notice that the inside is a polynomial. And that is actually going to be the same exact thing as doing a direct substitution, or will allow me to do the direct substitution. And when I do that, this is going to be the answer for the limit. Now, I don't know what that answer actually is. Like, I don't know what number that is, because that totally depends on what c is. However, I can see what's going to happen when I plug in c to the function in general. Remember, this is how I check to see if a function's continuous. I check its limit, and I check its y value. So let's see. The limit of f of c, or sorry, just f of c itself is actually going to look like 9 minus c squared. So notice the limit turned into this value, and the y value was this value. So we can see that f of x is continuous at c. But notice c was any number in -3 to 3. So f of x is continuous on the interval -3 to 3. Instead of choosing specific values to test, we kind of chose an arbitrary value, which essentially allowed us to check every value in the interval at once, right? Like no matter what number we would have picked, this argument would have always been the same. So we kind of checked every possible number in the interval at once. That's pretty awesome. Okay, well, we still have a couple more things to check if we want to show that this function's continuous on the closed interval -3 to 3. We would have to check that the function is now continuous from the right at a, at my starting point. So I need to go ahead and check that as I move over towards 3, which would be coming, or -3, which would mean coming at it from the right side, I need to check it's continuous there. So remember what that means. If I want to show if something's continuous from the right, I just need to show that the right-handed limit is equal to the y value. Now fortunately, we should be able to do this really, really quickly. So we'll note this. We'll say that the limit as x approaches -3 from the right of our function is really just saying the limit as x approaches -3 from the right of the square root of 9 minus x squared. We can go ahead still and do the limit of the inside, because I can use the same limit laws. The inside's a polynomial, so I can just directly substitute. So this is going to turn into 9 minus -3 squared. And that's going to turn into 9 minus 9, or square root of 0, which is 0. We can also see, though, that if I was to plug plug -3 into my function f, I would actually get the exact same thing. Square root of 0, which is 0. So f of x is continuous from the right at x equals -3. We're going to have to do the exact same calculation to show that at +3, my function is continuous. Notice again, now I'm going to have to say if I want to approach +3, I got to come at it from this direction, so that's from the left side, and I'm going to check what's the limit here and the y value there and see if they come out the same. Now, most of this work here is actually really, really simple. Let's see what we come up with this time. Hey, look at this. Again, I'm doing the limit of a radical, so I can just do the limit of the inside part. And the inside part's a polynomial, so again, I can just plug in the value of 3. So I'm going to have 9 minus 3 squared. I get square root 0, which is 0. I can also then calculate f of 3. Remember, I need to check to see if these two things are equal to get continuous from the left. But of course, this is just going to produce 9 minus 3 squared, which is just going to turn into square root of 0, which is 0. And so f of x is continuous from the left at x equals 3. Okay, so notice that I've kind of met all three of the criteria. And so I can make a final conclusion. Therefore, f of x is continuous on the interval -3 to 3, which includes the endpoint. There it is. Now I'll point out again, can you notice how many words I am having to use as I attempt to explain what I'm doing? This is not just a Calculus 1 idea. Hopefully you've had instructors in the past that have been using lots of words to help kind of explain their thought process to you, and they've hopefully been asking you to do the same. If not, they've potentially done you a slight disservice, because all of Calculus 1 is going to require that we can write things and just explain what we're doing as we're doing it. Calc 2 is going to demand that even more, and for those of you who might be going on to take Calc 3 and classes beyond, the writing is going to be immense. You're going to be doing a lot of writing and explaining. So the earlier you're able to kind of get into that habit, the better. You're just going to make your future self a lot happier because things will be easier. Hopefully with all of the writing here, it becomes a lot easier to go back and remind yourself of what we were doing. And so this is a problem that hopefully you can review to see how exactly we showed that a function was continuous on a closed interval.